Now that we've talked about the sampling distribution for the sample proportion, we can go ahead and conduct point and interval estimates for a sample proportion. Now again, without additional information, the single best guess for the population proportion P is the sample proportion P hat. In the same way that, as before, the single best guess without additional information for that population mean is that sample mean. So the z-interval estimate or confidence interval is given by the same formula as before. The standard error is denoted in a slightly different way, but it's really just sigma divided by the square root of n. So we take our point estimate for that population proportion, p hat, we add and subtract z alpha divided by 2 times the standard error, where the standard error is p times 1 minus p divided by n, and you take the square root of that quantity. Again, typically we don't know that population proportion p, so we will use p hat as an estimate when we're calculating that standard error for a z-interval. So let's look at an example of health insurance. Suppose you're a public health researcher and you're interested in why some people in the United States don't have health insurance while others do. So you gather data on employed people from the American Community Survey. It's a random survey conducted every few years by the U.S. government. And you might ask, what proportion of Americans lack health insurance among those who are employed? This is the ACS data, the American Community Survey data set. This is actually a subset of the actual data set, but it is real data. These variables are characteristics of respondents, and the cases, the rows here, are different respondents. The sample size is 343 people. So we're going to have a point estimate for the population proportion. We're going to use p hat for that point estimate. So to calculate the z-interval, we need that point estimate. So we obtain the following from our sample, right? The proportion with health insurance in our sample is 0.88, and the proportion without a sample is 0.12. So about 12% of people in the sample do not have health insurance. The z-interval estimate, right, is going to be based on that point estimate. So you should keep in mind here that the point estimate is 0.12, not 0.88. We could do a different kind of z-interval, but in this case, we're really interested in those people without health insurance. So we're using 0.12 as our value of p hat. And this, again, highlights the point that how we define successes and failures, it differs depending on the context. In this particular instance, we're defining a success as not having health insurance. And success, of course, should be in quotes. But now that we have this point estimate of p hat, 0.12, that's our single best guess without additional information for that population proportion that we do not observe. Well, using the fact that the sample size is 343, we can calculate a standard error. So we plug in p hat as our guess for p, and the standard error we find is about 0.0175. Again, that's just the standard deviation that we think is going on for that sampling distribution. So using an alpha level of 0.05, we have a z alpha divided by 2 value of 1.96. That's just locating our endpoints on that standard normal distribution. And so we can have this 95% confidence interval. We take 0.12, add and subtract 1.96 times 0.0175. That interval estimate, that z-interval, gives us a value of 0.0857 to 0.1543. So we'd say we're 95% confident that the true proportion of the population of employed people without health insurance is about 8.5 to 15%. Right? So to interpret this interval, all right, we're quite confident that this is 95% confident that that proportion is somewhere in that interval. But the thing is that this is probably an underestimate, right? Because if you recall, initially we were interested in the proportion of Americans in the population who do not have health insurance, but this is a data set of only employed people. So, in fact, this has probably been inflated. The proportion of people who do not have health insurance is probably higher. So a few things to know when we're dealing with sample proportions. Given the success-failure condition holds, the sampling distribution of a sample proportion will be approximately normal. Because of that, we can use one-sample z-tests and z-intervals for making inferences about a one-sample proportion. The success-failure condition, right, it's especially likely to fail with smaller sample sizes. Right? The success-failure condition is really a function of the value of p in the population and n. And since we don't know p, a larger n, right, makes it more likely that we'd expect the number of successes and number of failures to be greater or equal to 10. And with that, we conclude our first part of our discussion about sample proportions and making inferences about sampling proportions.